this lecture, we take a look at calculating the work done by the spring force, and then using that calculation with the work energy theorem to ultimately describe an oscillation. Once again, an oscillation is an extremely important type of motion. We're going to see it extensively later on in the second semester, and it's the starting point, for example, when describing energy transport with respect to waves. However, we take a look at oscillations first, and we do so here in this context by using the work energy theorem. Okay, now the spring force is a non-constant force. Because of that, this then means that calculating the work done by that force involves, strictly speaking, the methods of calculus. It involves an integral. Of course, this is an algebra-based course, but there is a mathematical workaround around the calculus. Okay, now in order to begin to describe how to calculate the work done by the spring force, when I demonstrated this in my previous lectures, I ultimately set up a vertical oscillation just because it's easy to do. However, what we're going to do here is we're going to remove the complication of the force of gravity. So then therefore, what we're going to do is just examine an oscillation that occurs horizontally on a horizontal frictionless surface. The spring will be idealized. If we then draw out the situation, first of all, here is once again a brief redescription, if you will, of Hooke's law. Okay, so for a horizontal situation, we always draw the following. We draw, first of all, a wall that the spring itself is attached to, like so. And then right here is the mass M, and the spring, if you recall, has a spring constant K. Recall that the spring constant K is an empirical property of a spring. It's basically a measurement of how stiff or how loose a spring is. Okay, because this is all going to take place on a horizontal frictionless surface, we usually don't even bother to draw the surface itself. Okay, now let's assume that right here is the equilibrium position. And then recall that there is no physical difference between stretching and compressing a spring when dealing with an idealized spring. So then therefore the following two pictures are identical. For example, let's say that I stretch out a spring like so, and I do so from the equilibrium position. The distance that we stretch out the spring or displace the spring from equilibrium is referred to as x. Okay, and then the spring force itself always acts back towards the equilibrium position. The spring force, call it F spring, is an example of what is called a restoring force. A restoring force always tries to restore the object back to equilibrium. The magnitude of that force is equal to the spring constant K multiplied by the displacement x. So as an oscillation occurs, for example, as x changes, this then means that the spring force changes, and it's therefore not a constant. Okay, now this is a picture that shows out stretching a spring. Here is a physically identical picture that shows compressing a spring. Recall once again that stretching and compressing a spring are considered to be identical to each other. So let's say that right here is a picture that shows us compressing the spring. So right here is the equilibrium position. Here's the displacement x. Okay, now the spring force still has the same magnitude as before, k times x, but in this case it points in the opposite direction on my diagram, because once again the spring force is an example of what is called a restoring force. It tries to restore the object back to its equilibrium position. So then therefore in this particular case, when compressing the spring force acts in this direction like so. Once again, its magnitude, however, is equal to k times x. We consider these two pictures here to be physically identical to each other. Once again, there is no difference between stretching and compressing a spring. Okay, now here's how we kind of get around the calculus, if you will, when calculating the work done by the spring force. So let me do a little bit of erasing here. Right here is just a basic description of the spring force itself for this horizontal situation. Okay, so calculating the work done by the spring force. Okay, let's calculate the work done by the spring force when I say stretch it out, say from equilibrium, or alternatively compress it. Once again, both of those pictures are identical, but let me just draw one of them. Okay, so what we'll do is we'll start right here at the equilibrium position, like so. And then we'll stretch out the spring in this direction like so on my diagram from equilibrium. Okay, so then therefore the displacement vector is in this direction like so to the right-hand side of my diagram, and the displacement vector has a magnitude of x. And then right over here at this position, the spring force is acting in this direction, F spring, with a magnitude of k times x. But as we're displacing the spring like so from equilibrium and x changes, the spring force changes. So then therefore, as I mentioned, we would, strictly speaking, have to use the methods of calculus to calculate the work done by that force. Here's how we algebraically get around this problem. What we do is we calculate the dot product between the spring force and the displacement vector, but we do so by using the average spring force. The average spring force as we go from equilibrium to this position here. Now recall, of course, how you calculate an average. That is, you add up the amounts associated with the forces in this case, and then you just divide by the number of forces that you have. In this case, we're just going to have two. Right here, the spring force is equal to 0, and right here, the spring force is equal to k times x. So the average, I'm going to call it F bar spring. Okay, let's note this in your notes. This is the average spring force. That's going to equal 0 plus kx divided by 2. The spring force is equal to 0 here, and it's equal to kx here. So then therefore the average is equal to kx over 2. This is the quantity that we use a dot product with in order to calculate the work done by the spring force. Okay, so the work done by the spring force now is going to be the following. It's going to be the average value of the spring force multiplied by the displacement vector, and then multiplied by the cosine of the angle between these two vectors. The spring force acts to the left-hand side of my diagram, the displacement is to the right-hand side of my diagram, therefore there is a 180-degree angle between the two. Cosine of 180 degrees is equal to -1, so then therefore, if we plug in, we get 1/2 kx squared, like so, with a negative sign. Let me clean this up a little bit, like so. Okay, the reason for this is because F spring, recall, is, or F spring average, excuse me, is kx over 2. We then multiply by x and then multiply by cosine of 180, which is equal to -1. And then therefore the work done by the spring force when stretching it out, or alternatively compressing it, is -1/2 kx squared. For those of you that are in calculus or have some experience in calculus, what I actually did was I integrated kx over the variable x. In doing so, you end up with this quantity here with the proper limits of integration to show the work done by the spring force. But for this algebra-based course, I'm dancing around that calculus by using the average value of the spring force between here and here. Okay, now this is the first situation that we'll look at. In the second situation, what we'll do is start here with the spring already stretched out and then move the object back to the equilibrium position. We'll calculate the work done by the spring force in doing so. So let me do this on the lower board. Let's call this situation 2. Okay, so right here, for example, is the equilibrium position. And now what we're going to do is we're going to displace the object back towards the equilibrium position like so, the displacement s. In this case, notice that the spring force points in the same direction as the displacement vector. So in doing a dot product when calculating the work done by the spring force, we're not going to have a 180-degree angle like we did on the top board. Instead, it's going to be a 0-degree angle. The average value of the spring force as we go from here to here, let me just draw another diagram to show that where we are when we end up, is once again the equilibrium position like so. Well, the average value of the spring force between here and here is once again just kx over 2. It always will be for the situations that we look at when having the spring stretched out and then moving back towards equilibrium, or up on the top board starting at equilibrium and then stretching out the spring. In either case, the average spring force is always just going to be kx over 2. Once again, we're dancing around some calculus here in these versions of these calculations. Okay, so the work done by the spring force then, therefore, is going to be the average value of the spring force, kx over 2, multiplied by the displacement, and then multiplied, as I said in this case, by the cosine of 0 degrees, which is +1. So then, therefore, the work done by the spring force is +1/2 kx squared. Once again, I'm dancing around an integral here with the proper limits of integration. We would then find that the work done by the spring force is this positive value. So for our purposes in this algebra-based course, the work done by the spring force is either going to be a -1/2 kx squared or +1/2 kx squared. Those are the only scenarios that we'll look at. It will be positive if there is a 0-degree angle between the force vector and the displacement vector. It will be negative if there's a 180-degree angle between those two vectors. Those are, once again, the only situations that we'll look at. Okay, now let's immediately calculate, or rather incorporate, the work done by the spring force into a calculation involving the work energy theorem to describe an oscillation. I have this set up as a problem. Let me go ahead and do some erasing here on the board first, however. And then I have the problem on the screen. Let me put the problem on the screen, like so. Okay, and then copy it down into your notes as I read it here. A mass of 1 kilogram is attached to a spring with a constant of 50 newtons per meter. It initially stretches the spring 0.5 meters from the equilibrium position on a horizontal frictionless surface. The mass is released from rest. Use the work energy theorem to calculate the speed of the mass as it passes through the equilibrium position in part A of the problem. And then part B of the problem, then we'll figure out exactly how far it compresses the spring on the other side of the equilibrium position. In doing this problem, what we're going to begin to describe, very simply, is an oscillation by using the work energy theorem. Okay, now for part A. Part A, we begin with the spring already stretched out, like so. So right here is the equilibrium position, and then we're given the following values. The spring constant K is 50 newtons per meter. The mass of the object is 1 kilogram. And then what we're going to do is we're going to displace the spring in this direction like so. We're going to move the object back towards the equilibrium position, thereby releasing it from rest. So the initial speed is equal to 0. And then therefore, after we let go of it on the top portion of this diagram, the object will then pass through the equilibrium position like so with a speed v that we're asked to calculate. Okay, the spring force in this case, which is always back towards equilibrium, you'll notice is at a 0-degree angle with respect to the displacement vector x. So then therefore, when we calculate the work done by the spring force, just as I did a few minutes ago, it's going to be the positive 1/2 kx squared. Okay, let's go ahead, however, first and set up the work energy theorem. So net work equals change in kinetic energy. And then let's approach this much like we did earlier in the unit by looking at the right-hand side of the expression first. Recall that the right-hand side of the expression is always the same thing in the following sense. It's the final value of the kinetic energy, 1/2 mv squared, minus the initial value of the kinetic energy, which in this case is 0, because we release the object from rest. So the right-hand side of the expression is just the following, like so. And then on the left-hand side of the expression, we do our net work calculation. Immediately we can make some shortcuts. Because this is a horizontal situation, as we've seen before, no work is done by the normal force, nor is any work done by gravity. In addition to that, this is also occurring on a frictionless surface. So then therefore, of course, there is no work done by friction. And then therefore, the only thing that matters is the work done by the spring force. The work done by the spring force from our practice calculation a few minutes ago is positive 1/2 kx squared, like so. Okay, let me just go ahead and clean up this expression a little bit by just getting rid of this like so here in our notes. And now let's take a look at this expression here. Okay, this expression here is an expression of the energy transfer that occurs. And now, with this problem, you're going to begin to see hints of a new form of energy that is present. Always think of the energy transfer, as we've already described, as what form of energy becomes what other form of energy. So therefore, we already know, of course, what the right-hand side of the expression is. The right-hand side of the expression is the kinetic energy as the object passes through the equilibrium position. The question is, however, what is this? In other words, something that has to do with the stretched out spring is transforming into kinetic energy as the object moves through the equilibrium position. So imagine it like so in terms of this demonstration spring, and I stretch it from equilibrium. I then release the spring from rest, and then as the object would pass through the equilibrium position, it would do so with some kinetic energy. Therefore, this guy right here has to be a new form of energy that is present, and as we'll see later on, it's what is called spring potential energy. So like gravity, the spring force also has potential energy associated with it. We'll define this and describe it a little bit more carefully, however, at a later date. But for now, this is transforming into this. This right here is the kinetic energy of the object as it passes through the equilibrium position. And then this right here is a new term. I'm going to put a question mark here, however, associated with it, because as I said, I'll be a little bit more careful later on to describe it exactly. But for now, I'm using this problem to introduce you to the idea of spring potential energy, which in this case is transforming into kinetic energy as the oscillation begins to occur. Okay, now mathematically, what we have to do here is just solve for the speed v. So let me just rewrite the expression here. Like so. And now let's go ahead and solve for the speed v. So first of all, the 1/2s do cancel out here and here. But notice that the spring constant K does not cancel, nor does the mass M cancel. So those properties of the oscillator, its mass and the spring constant K, are important when describing the speed V. So to calculate the speed V, what we now have to do is divide the M to the other side. That then gives us this, like so. And then we take the square root of both sides now to get the speed V by itself. Let me just write that here, like so. And now we plug in our numbers. So let's go ahead and do so, and when you do, you end up with a speed in terms of meters per second. All right, so we have here the square root of 50 divided by 1, that's underneath the radical sign, and then multiplying by 1/2 meter for the displacement, and this comes out to be 3.54 meters per second. Okay, and now we get to part B. Part B asks us to calculate how far on the other side of the equilibrium position does the mass compress the spring. Before I even set up the problem and solve for the answer, can you tell me what the answer is? Yes, of course, it's going to be 1/2 meter once again. Here's, however, how we show that. Okay, so let's now go ahead and label this as part B. And then what we do to begin this portion of the problem is we're passing through the equilibrium position like so, and we're doing so with a speed V0 that's equal to the 3.54 meters per second that we calculated earlier in part A of the example. Okay, and then the end of the problem here, at the end of part B, here's the equilibrium position. For an instant, the object comes to rest like so. And then right here, from right to left, is the displacement vector x. This right here is the unknown, technically speaking, here in part B of the problem. Okay, now the spring force points back towards the equilibrium position always, like so. So then therefore there is a 180-degree angle between the force vector and the displacement vector. So when calculating the work done by the spring force here, it's going to be the negative 1/2 kx squared term because of the cosine of 180 degrees being equal to -1. Here's, however, how we set up the work energy theorem from scratch for part B of the example. So net work equals change in kinetic energy. Once again, deal with the right-hand side of the expression first. So the final kinetic energy is 0, and then minus the initial kinetic energy with the speed V0. So then therefore the right-hand side of the expression is going to look like this. And then the left-hand side of the expression is the work done by the spring force, which from earlier in this lecture is negative 1/2 kx squared. Notice that the negative signs will cancel out here in the expression, and then therefore you end up with this expression here, like so. This is once again a statement of the energy transfer that occurs here in this situation, in part B of the problem that is. And the energy transfer that occurs here is basically just backwards of what we saw earlier in part A. So in this particular case, all the kinetic energy that we have here at the beginning of part B, as we pass through the equilibrium position, is transforming into this new term, spring potential energy, as we compress the spring. So this becomes this. So this right here is the initial kinetic energy as we're passing through equilibrium. Once again, this is for part B of the example. And then this right here is this new term. I'm going to still keep a question mark associated with it. We'll eventually get rid of that question mark, but for now, I'm just using the example here to introduce you to the idea of spring potential energy. Okay, now mathematically, what we have to do is solve for x here. However, in doing so, notice that this expression here is basically the exact same thing as this expression here. It's just the energy of transfer occurs backwards. So then therefore, if we were going to go through the motions and solve for x, what we would find is that x is equal to 1/2 meter. No surprise. So then therefore, as long as there is no friction and the spring is idealized, there is no heat loss in the spring, then this object will oscillate forever in this manner. It will alternatively stretch and compress the spring 0.5 meters from equilibrium every single time, and it will always pass through the equilibrium position with a speed of 3.54 meters per second. The object will execute an extremely important type of motion that is called simple harmonic motion. The object itself is what is called a simple harmonic oscillator. Let me write that out for you here. So the object will execute or undergo what's called simple harmonic motion, which is abbreviated, by the way, as SHM, and the object itself is called a simple harmonic oscillator. A simple harmonic oscillator which is abbreviated as SHO. So to summarize the spring force, we teach the spring force backwards to students. Normally, when you are taught forces, you are taught how to deal with them by using F equals ma first, and then, as we have seen, the work energy theorem. By and large, that's what we've done here, for example, in the first semester of the course. However, when it comes to the spring force, we teach it to you backwards. We teach you how to deal with it, first of all, by using the work energy theorem, because even though I'm dancing around some calculus, it's actually an easy calculation to make. However, a little bit later on, specifically in the second semester, you'll see exactly how F equals ma works with simple harmonic motion, giving rise to this example that we've seen here. Okay, let me go ahead and conclude this lecture here.